Hi, everybody. Um, we did it. We passed, test number 2, and we're moving into the final major section of Calculus 1. That means we're going to be doing the opposite of differentiation. Uh, this first section is labeled antiderivatives, but if you haven't already, go ahead and take a look at the first 9.5 minutes of this video about integration and the fundamental theorem of calculus, because we're going to be talking about integrals, and this is a great introduction with lots of cool animations. So if you've watched that, great, and we'd be ready to go. But if you haven't, go ahead and watch it. All right, so section 4.7. We are going to be investigating a type of integral called an antiderivative. And yeah, throughout the rest of this course, we're going to be looking at about 3 different flavors of integral. The first one, well, here, let's just call it, antiderivative. Oh, and that's really small. Give me a second, guys. Antiderivative, or we could call it an indefinite integral. Those are really synonyms. The notation that you'll see for this will be one of those long S's, and inside of that you'll have some kind of function, normally of x or t perhaps. But yeah, there won't be any bounds of integration on the top or bottom. That'll just be left blank. And we've got our differential over here, dx, giving us the height and the width of little rectangles that we're going to be summing up. So that's what we're looking at today. This is the notation for today. Later on, we're going to be looking at area functions. And it's not a bad idea just to give you a little bit of an advanced organizer here. This one, well, area function. This is the weirdest of the bunch, probably, but where you've got a constant bound of integration on one part, and then a variable bound of integration on the other part, and you'd have some function here. But yeah, this will actually give you a new function, f of x, that gives you an area going from 1 to some movable point x. And that's kind of why I call it area function. And the last one, the definite integral, that's what you saw with a solid starting point and ending point. And you've got some function on the inside. But this is one where you get a number, as a result, which would describe the area between the function and the x-axis. This one you get a function, and actually, I'm glad that I'm coming back up to this, because for the antiderivative, what are we actually getting when we do an antiderivative? We're asking ourselves, what kinds of functions give us this as a derivative? And so what we actually get here is a family of functions. Yeah. Normally just separated by some arbitrary constant, where we'll be able to slide that up and down the y-axis as we like. But when you would take the derivative of f of x plus c, that c would just go away because the derivative of a constant is 0. And so yeah, an antiderivative is going to give us a family of functions. An area function is going to be a function. And then a definite integral with 2 solid bounds of integration is going to give us a number. And so, yeah, we have the right to expect different things out of each one of these different flavors of integrals. But the first one up for today is antiderivative. We're going to be finding some families of functions here right now. Okay, moving on to example 1. Finding antiderivative, and it's saying find an antiderivative, meaning pretty much any of the members of this family of functions would work. But yeah, we're going to include the whole family. We're going to get used to writing plus c. So yeah, for this one, and I'm going to write capital F of x just to denote that we've found an antiderivative of little f of x. I kind of think of this one as the parent function, and this one as the child. But yeah, undoing the power rule here, we would be adding 1 to the exponent instead of subtracting 1 from the exponent, and then dividing by that exponent. So I mean, if we wanted to show that out, I guess we'd have divided by 3, but I mean, really that's just going to be x cubed. Yikes. So yeah, undoing the power rule gets us an antiderivative there. And yeah, all along the way, it would have been good for us to write a plus c. I guess I didn't put the GeoGebra link on here, but I'll be able to pull it up soon. Here, actually, I'm going to do it right now. GeoGebra link and put it in. But the idea here is, we've got our parent function, big f of x, and in GeoGebra, I defined little f of x as big F prime of x, so little f is the derivative of this. And notice that no matter where we change c, this constant that we're shifting our antiderivative by, the derivative stays the same. Because, when you take the derivative of c, it's just going to go to 0. And so the antiderivative really is a whole family of functions that all look like this. And, no matter how we shift it vertically, the slopes at any given x value don't change, so that derivative doesn't change. Okay, so that was the first one. And I've got that so that I can paste it in here so I don't forget to. Again, oh geez. Give me a second. Boom. Okay. So that's antiderivative number 1. Part B. Here we've got sine. So we've got to think which function would give us a derivative of sine. And the answer to that would be negative cosine. Yeah, because g prime of x would be sine. And yeah, adding a plus c there would be good too. And then finally, looking at part C, we would think what would give us a derivative of 1 over x? And that would be the natural log for that part. And then what would give us a derivative of 5? Well, that would be 5x. And we could add a plus c to denote that we've got a whole family of functions. We could shift this function up and down. Cool. Those are antiderivatives. And yeah, there are many formulas that may or may not be helpful to you. I mean, really every time I do an antiderivative, I think I've memorized things mostly according to the derivative rules, and then I'm just undoing those derivative rules when I take antiderivatives. Yeah, I mean, this is what it looks like to have a constant multiple of a function. That constant multiple just stays along for the ride. Um, Here's if you're taking the antiderivative of the sum of two functions, it's just the antiderivatives of them added together, like you'd expect. Uh, Here we've got the inverse of the power rule. On this one. So instead of subtracting one from the exponent and multiplying by that exponent, you are adding one to the exponent and then dividing by that result. 1 over x becomes the absolute, or the natural log of the absolute value of x, because 1 over x has a larger domain than the natural log does. So putting those absolute value bars in is actually good. Here we've got e to the kx. So on this one, we get our first experience with the chain rule a little bit, because we've got that k up in the exponent. And so 1 over k is coming out, again, because we're undoing the chain rule. Normally, if you were just doing the chain rule, you'd get k times e to the kx. But undoing the chain rule means that we get a factor of 1 over k. And, same kind of thing with these exponential expressions that aren't e as a base. You end up getting, well, actually, it's worth noting that, when you do this, you get that 1 over k factor, and you get the 1 over the natural log factor, like you normally would have a natural log factor. Anyways, that's great. And here's some justification for why that works. And so those ones we're going to use all the time. We're just undoing differentiation. Here's some more for the trig functions. We've got, all of the antiderivatives that end up leaving us with things like cosine or sine or tangent or cotangent or secant or cosecant. We're looking for things that we can undo. Here are the arcsine, arctan, arcsecant. With these kind of expressions, get us back to that. We're going to be doing more of these kind of integrals with the inverse functions in calculus 2. Well, you guys will be doing that in calculus 2. And so, those are just the inverses of the derivative rules. Let's take a look at example number 3 and try to practice this. If you guys want to pause and see if you could do this on your own, I would be happy if you wanted to try that out. You don't have to. Okay, so taking the antiderivative of part A, we've got x to the negative 1/2 minus the cosecant squared of 5x. So undoing the power rule means that we would be adding 1 to the exponent and then dividing by that exponent, which eventually that would just give us 2 times, well, we could just write this as the square root of x. Which that makes sense, right? Because this is 2 times the derivative of the square root of x. Normally there would be a 1 over 2 square root of x. Anyways, that one's good. And then this piece minus, undoing that as a derivative, the cosecant squared is the derivative of the cotangent, right? Yep, okay. And there's going to be a negative sign involved here. So I'll make that into a plus sign. We're going to turn this into a cotangent of 5x. And then due to the chain rule being reversed, I need to multiply by a factor of 1/5. And for good measure, we can throw in a plus c. But yeah, there's an, general antiderivative here. And I think, there is, maybe this is the technical difference between a general antiderivative and an antiderivative. We probably didn't need to put the plus c's on this one. We could have put anything there, but we probably didn't need to put plus c's there. But for a general antiderivative, putting the plus c at the end is important because that denotes the family of functions. Anyways, going back to g of x, I'd probably want to do a little bit of rewriting on this one too. This one I would divide through by 2x so that we get 7/2 x to the 1/3 power plus 3/2 x to the negative 1/2 power minus 2 to the x power. Okay. For these first two, we're just reversing the power rule. So we would get 7/2 x to the 4/3 power divided by 4/3 plus 3/2 x to the 1/2 power divided by 1/2. And then for this last one, yeah, we're undoing this exponentiation, which means we're going to need to divide by a natural log of 2. And so, yeah, I mean, this probably could be cleaner. On the top, I think we'd have 21/8 x to the 4/3 plus 3x to the 1/2 minus 2/x over the natural log of 2. Okay, that looks well enough for me at least. Cool. All right, moving on. Lots of examples here, and I'd like to start talking about Riemann sums. So, example 4 is, bringing us back to finding relationships between position, velocity, and acceleration. Here we have a ball being thrown straight up in the air at 64 feet per second by a person standing on the edge of a platform. The moment the ball leaves the thrower's hand, it's 96 feet above the ground. Got a nice diagram. On its way back down, the ball misses the platform and hits the ground. When does the ball reach its maximum height? What is that maximum height? When does the ball hit the ground? Okay, those last 3 questions, maybe I'm not so interested in. I mean, once we figure out what the function is, you guys should be able to do that. You should be able to find a maximum height. We've just been maximizing stuff. You're going to be great. What I want to pay attention to is the relationship between those 3 layers of functions. Acceleration, position, acceleration, velocity, and position. Because right now, what we've actually been given is a couple of initial conditions. This first part, the 64 feet per second, I might label that as like V0, because that is the initial velocity at which this thing is being thrown straight up. 96 feet might be something that I call, let's call it P0 for position 0. Might be H would be fine, but yeah, position 0, 96 feet above the ground. We haven't been given any information about acceleration, but if this person is working on Earth, then we do know about how this ball will be accelerating. It's going to be due to gravity, right? So let's go ahead. And, I guess really this is using more derivatives rather than antiderivatives when we start from the acceleration function and then bring it down to the position function. But we will see, again, I mean, it's the same kind of thing. The acceleration is going to be negative 32 feet per second per second. Oh my gosh, I just wrote 2 twice. Yeah, negative 32 feet per second per second. And then, oh, actually, we do need to take an antiderivative here because the acceleration function is the derivative of the velocity function, or it's the second derivative of the position function. And so, yeah, we're right where we want to be. For a second, I doubted it, but I shouldn't have. Let's move this over a little bit. Okay. Yeah, we're looking at a derivative here when we're looking at acceleration. So if we take an antiderivative, that first one would be, let's go purple. The velocity at time t would be negative 32 times t. We're undoing the power rule there. And then we would need to do a plus c. But in this case, you know, maybe I'll just write it like this. That plus c is always going to turn out to be a very special plus c. We're actually given information about the initial velocity. And notice if you put in 0 in for time, this negative 32t part just goes completely away. And so, you know, the velocity at time 0 would be just c, or just, you know, v0. So, yeah, when I actually write this out, I'm going to erase that. Yeah, we get negative 32t plus velocity of 64 feet per second straight upwards. Cool. All right, so now that's our velocity, and the velocity is the derivative of the position function. So when we get to the position, we need to take another antiderivative. And if we do an antiderivative here, we'd get negative 16t squared plus 64t. And then we would be adding a plus c, but just like in the other case, if we put in t equals 0 into this so far, all of that turns into 0. So our initial position, I'm just going to write it right here, will be 96, our, you know, P0. So having information about the second derivative and then 2 initial conditions at the velocity and position levels allows us to get a quadratic function that describes the height of this ball at any time t. And once you know that, you can do the maximum height, or when does it reach that, and all that good stuff. I'm not concerned with that. But here, we use antiderivatives twice. Example number 6 here is a graph where we've been given a graph of the derivative, and we're looking to sketch the graph of f. So we've been given a graph, and notice we have another, you know, not really an initial condition here, but we at least have an anchor point to position our antiderivative, so that we're not talking about the entire family of functions. We're actually just going to pick the specific function that goes through this point. So let's try to do our best with a sketch here. What do we know? We need to go through the point 1, 2, which on this graph is about here. So I'll try to mirror that. I think the y-axis is a little bit squished, but that's good. So we want a point to go through here. Let's make this red. Nice. Okay, so that's an anchor point. And let's think about Is there a specific antiderivative way that we would want to think about this? Or am I just going to, look at the y values over there and think about slopes over here? I think that's probably what we need to do. All of the y values that we see over here are going to be slopes of this function. So that, this would correspond to an interval of decrease, an interval of increase between C and D here, and then an interval of decrease over here. And at 1, it looks like we're at the top of this upside down parabola. That's going to be an inflection point. It's going to be the part of our graph f of x that will be the steepest, at least the steepest in a positive direction right there. Actually, and the slope will be 8. So there's no hope of me getting something that's exactly 8, but we've got something that's a fairly steep positive slope at this point. And then it would slowly curve down to a slope of 0 when we get to C. So, I don't know, we'd be aiming for a flat slope here. So maybe I sketch that there. And then we'd be aiming for a flat slope at D. And D's, over here somewhere. And we'd get a flat slope there. So, okay, we've at least got the part where we are on an interval of increase. And then, like I said, since we've got negative y values over here, we're going to have negative slopes here. So this one would go like this. This one would go down like this. And something that looks like a quadratic function turns into something that looks like a cubic function. Cool. Nice. Okay. Nice little exercise. Okay. Here we are stepping into section 5.1, and we're going to do this for about the next 13 minutes. We're going to be riffing off of this example pretty much the entire time. So the problem here is we have a function f of x equals x squared. Boom. Y equals x is given there as a reference. So this is going to be a relatively small amount of area that we're trying to find, but we're trying to find the blue area. And right now, we do not know how to take a definite integral, even though, later on, we will set this up as the integral from 0 to 1 of, well, I could just write x squared instead of f of x dx. Like later on, we will set up this definite integral and we will go through a series of short steps where we find some antiderivatives, use the fundamental theorem of calculus, and get a number answer. It'll happen really quick. Before we do that, though, we need to go through the motions of kind of discovering how to do this and do the hard work of eventually getting to the limit definition of an integral. And so in service of that, the first thing that we're going to do is approximate. And approximations of integrals are called Riemann sums. First, we're going to approximate the area with 4 rectangles. Now, you saw in the video that we have some freedom in how we set these rectangles up. This first example that I have here, we're splitting up the interval from 0 to 1 into 4 equal sections. So each one of them are, 1/4 of a unit long, or at least wide. And then the height of each of these rectangles for a right-hand Riemann sum is given to us by the right-hand endpoint of that interval. So here we use 1 as an x value and follow that all the way up to the function x squared. So we get 1 squared here for a height, or we get 3/4 squared for a height here, or 1/2 squared for a height here. Yeah, we're using the right hand of each interval as our sample point to find the height of our rectangles. So the right hand Riemann sum, for on the interval from 0 to 1, we're always multiplying by some change in x values. This 1/4 is just the length of our interval in the x direction. And then we're always multiplying by the function evaluated at some sample point. So yeah, this part you could think of it as, f of 1/4 and f of 2/4 and f of 3/4 and f of 4/4, which is 1. I kind of went off the place there, but yeah, we're just adding up a bunch of areas of rectangles here. And yeah, the right hand Riemann sum is an overestimate because we're always using the right hand, and this is an increasing function. So yeah, our rectangles are taller than the function there. For the left hand Riemann sum, we're using the left endpoint of each interval to determine the height. And so since this is an increasing function, we're getting an underestimate for the left hand Riemann sum. Yeah, the major differences to highlight there, I mean, the delta x, the change in x values is always the same, 1/4 in each case. It's just that now we're offset. We have this new term 0 squared times 1/4. And then you see the same 3 terms being repeated here and here and here. So yeah, we get an underestimate with this one. And so we can be confident, while we don't necessarily know the exact value of this integral, the exact blue area, we know that it's in between 0.46875 and 0.21875. It's somewhere around 0.3-ish, probably. And if we wanted to get better estimates, we would shrink our delta x. We would make that smaller, increase the number of rectangles that we're using, and make a finer mesh. So if we use more rectangles, just to clue you in on what these letters mean, I think we're using O for overestimate and U for underestimate. But this is the right-hand Riemann sum. And yeah, this one's the left hand Riemann sum. That was the underestimate. And then this is the difference between the two estimates. So yeah, up here, when we just used 4 rectangles, the difference was about 25, like 0.25-ish. Yeah, actually exactly 0.25. So about a quarter different. And notice how the difference between the overestimate and the underestimate continues to shrink as we increase the number of rectangles. So here we're using 10, 100, 1,000 rectangles for this entire time. And this is actually something special called the midpoint rule, where if you're taking the average, or actually, this would kind of be the trapezoid rule. Not important at this point. But yeah, when you take the average of the overestimate and underestimate, it's likely that you would be getting pretty close to the actual answer. And so the entire time, this has been pretty close to 0.33, 0.3333, 0.3333. Even here, you know, in the overestimate or underestimate, once you get to 1,000 rectangles, these individually is approaching 0.333, you know, even in themselves. So using more rectangles gets us a more exact answer. And indeed, when you look at the definite integral, this thing does end up being 1/3 in the end. How we get to that, we still are going to work at. We're probably not going to get through the entire, we're not going to get through the entire limit definition of an integral today, but it would be worth it if we started to look at sigma notation. Get a feel for how to express sums in this way, because looking at this notation will help us understand the limit definition of an integral better. So like I said, yeah, this letter is sigma, and you know, that stands for sum because, you know, sum starts with an S. Yeah, and what the sigma notation does is allows us to concisely express a sum of a lot of things. And it's, you know, even better and more concise kind of compared to really long sums of things. In this case, what we have is just the sum 1 plus 2 plus 3 plus 4 plus 5. And how that's encoded in sigma notation is I is called an index, and this is the start value of the index. So we're going to start at 1. And so that means for our first time through the sum, we're going to put in 1 for I. And then that's really all we'd have to do. And then we'd be able to click over to the next one and put in a 2 next. If you've ever done any computer programming, this is going to be a lot like a for loop, where you keep going through the thing, but every time you increment by 1. And the idea with this for loop is that we would start off at 1, plug it into here, and we would keep going through the for loop until we get to 5. So the idea is, yeah, 1 plus increment, put in the 2 plus increment, 3 plus 4 plus 5. And, you know, once we get to 5, putting 5 in for I, we stop. And so, yeah, the 5 is where we end. Let's just call it ending index. Index value. Okay, ending index value is up at the top. Cool. All right, so for that one, hopefully that's relatively straightforward. On this next one, we've got a little bit more of a challenge. We've got definitely still a summation because we're alternating between minus and plus and minus here. We've got a product on the inside. And the pattern that we see is 4 times 5, then 5 times 6, then 6 times 7, then 7 times 8. And in order to encode that in sigma notation, you know, we could write this differently, and I will write it differently soon. If we want to get into the habit of starting our index at 1, then starting at I equals 1 would be fine. And in order to get that first number to be 4, we would need to take I plus 3. And in order to get this second number to be 5, we need to do I plus 4. And in order to get the alternating sign, we can take a power of -1, where this I is still an index. It's not an imaginary number. But yeah, having this hanging out in the exponent of -1 is, it's going to be nice because whenever we put in an odd value of I, the exponent will be even, and we're going to get just a 1 out of this. But if we get an odd exponent of -1, we'll have a negative. So yeah, plugging in 1 gives us 4, 5, and then +1, and that's why we get a positive 4 times 5. And then if we put in 2, we would get 5, 6, and -1 to the third power, which would still be -1, and that's why we get a -5 times 6. And then after doing that a couple more times, we end off at the index ending value of 4, and we're done. An equivalent way to write this one that might be a little bit easier, instead of starting off at an index value of 1, we could start off at an index value of 4, because, I don't know, that first number that we see is 4, and maybe we decide to end at 7. But then we would just be taking our index and multiplying it times the index plus 1, and then, we would still raise -1 to a power. I'm running off the screen here. The power on -1, we would want to match the sign. We would want this to be an even power first. So if we just put I up here, that would be fine, because the first number that we would put in is 4. So yeah, we would get 4, 5, and then -1 to the fourth power, which would just be 1. And we would get that first term like we want, and then it should work after that. But yeah, those two summations are equivalent, just starting at different indices. All right, I think that's probably where we're going to end. To give you a preview of what's coming up next is we're going to express our Riemann sums as summations. Then we are going to talk about splitting this up into rectangles and then taking the limit as n goes to infinity. It's going to be great. And finally, after doing this limit definition and looking at some summations and stuff, we're going to get to the answer of 1/3. It's going to happen. And then after that, we're going to look at the definition, the limit definition of the definite integral. And we're going to be on our way. All right. So I will see you tomorrow, and we'll talk about that stuff. It'll be great. Have a good rest of your day. Bye.